All right. So we've mentioned this briefly in passing a couple of times throughout our chemistry careers, but what we're focusing on at this point is making sure that we understand that when chemicals react, this is because they collide. And the strength of their collision, or the amount of force in that collision, depends whether or not the reaction will occur. Additionally, the angle at which the collision occurs depends on whether the reaction will occur. So this angle, getting the correct angle, is really just a chance setting. And so a chance condition, right? So if you have two reactants that need to collide a certain way, and they can't collide different ways, you just need to increase the opportunities for them to collide those different ways. Now, if I have, and I've talked about this briefly as well, but if I have A and B going to C, for example, and I have a catalyst, a biological catalyst, something that has, an enzyme, we call these biological catalysts, something that has a spot for my A to fit in and for my B to fit in. And when those arrive, if the enzyme wiggles just enough that new bonds can form and old bonds can break, creating the product, right? Then this reaction can be catalyzed because all these needs to arrange properly and come into collision with the right energy is promoted by the catalyst, right? The binding brings them in the correct proximity, holds them tight. The motions of the catalyst allows those new bonds to be formed much easier, okay? And that will speed up a chemical reaction dramatically. Now, what keeps reactions slow is the requirement for the reactants to have enough energy to break and form new bonds, break the previous bonds and to form the new ones, all right? And we have this video here that kind of talks about this.
If oxygen and methane molecules are mixed together in the same container...
Now, I was kind of talking a little bit, and I want to emphasize this anyways. The reaction that we're looking at here is oxygen and methane, CH4 plus O2. Do you know the products of that, Fred?
That's just combustion, so carbon dioxide and water.
Very good. Carbon dioxide and water. We have an organic compound that we're combining with oxygen, carbon dioxide, and water. Okay? Now, if you mix these two in a container, you won't have a chemical reaction, as was stated.
They collide, but there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form.
There's carbon
The
dioxide and
additional
water.
energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continually colliding but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
Okay, and that's one reason why farmers really appreciate lightning sometimes, because the resulting nitrogen that has been changed in terms of its oxidation state can come down with the rain then and supply nitrogen in terms of oxidizable nitrogen for the plants, right? So, the activation energy is the energy necessary to take our reactants to a point that they can slide down our energy diagram hill to form products, right? And I kind of think of this as your little molecules as marbles here. And if you roll the marbles, give them some energy, they'll kind of try to get over this hill. But if you don't roll them enough, then they won't slide down to get products. They'll just come back to reactants. If you provide them with this much energy, then they'll be able to roll back and forth, back and forth, back and forth. But they still won't be able to get over the bump and produce products. Okay? When we have a catalyst, what that does is it lowers this activation energy. So the line now would go something like that, so the reactants can more easily form products. So it's this activation energy that relates to the rate of the reaction, K being the rate of the reaction, for example. So here's an example of an energy diagram in which here are our reactants and here are our products. And in this case, some bonds need to be broken, new bonds are formed, but then some other bonds need to be broken, and then we finally get to products, right? And both of these represent activation energies. To get to products, however, you need this much energy, right? If I give enough energy to get this high, then my intermediate, we call it, would form, and it could go back and forth between intermediate and reactants, right? If it had this much energy, the marbles could roll back and forth easily. And so we would still get no products. And so the rate-dependent step would be getting over this activation energy. So these are our activation energies. This is what we call the activated complex. Both of these would be activated complexes, points at which you have a complex which is going to form something new, and it's at the top of some activation energy. So this is our product energy. This is our enthalpy of reaction, the amount of energy that's either going to be released or required. Now in this, do you remember, is this going to have a delta H of a positive value or a delta H of a negative value?
I can't remember. How can you tell?
Well, remember that delta H, change in H or change in any energy for that matter, is always products minus reactants. So if I take this value, products, minus this value, am I going to get a positive value or a negative value?
How do you know?
Well, this value is higher in number. So if we give this a number like 100 and this is 50, 100 minus 50 is going to give us a positive value.
Oh, yeah, okay.
Let's go back to the previous slide here, right? In this case here, products are lower than reactants, and so products value, whatever you give it, 50 here, 100 here, is going to be a negative value. So this is a delta H where energy is released.
Okay, yeah, I see that.
Okay, very good. So here's a potential energy diagram. Which one of these steps is going to govern the rate of the reaction, or be what we call the rate determining step from going from reactants to products?
Did you say the higher one?
That's right, because even though we have this much energy, until we overcome this second step, we're not going to get any products. All right, so the greatest activation energy is going to be the one that governs the rate of the reaction. Okay, now we have an ability with an equation here to relate the rate of reaction to the activation energy. And this can be done here where we have K, our rate constant, and we can, well, let's do this one first. We can relate this to some constants, the steric factor that's associated with the kind of chemical, the frequency of collisions, right? Also to a degree related to the kind of chemical, its shape, that sort of thing. We can combine those into one constant, A, but here we have Euler's number, E, raised to the activation energy divided by RT, where R is a gas constant that helps all of our units work out. And this is in joules per mole Kelvin. And so our temperature here has to be in Kelvin as well. Now, the rate of the reaction is related to the activation energy and temperature. R is a constant, A is a constant as well, and E is a constant as well. So This can be rewritten in a linear form in such a way that if we have two reactions at different temperatures and we get the rate constants for those two reactions at those different temperatures, then we can set up a scenario where identifying both rate constants and having both temperatures will give us the activation energy. Or if we know the activation energy and the two temperatures and one rate constant, then we can identify the rate constant at the second temperature. Now, it doesn't matter if this is K1 or K2 on top, but you just have to make sure that K2 corresponds to this one here and K1 corresponds to the one that's subtracting from K2. So here's an example. We get a K at 25 and a K at 50 degrees Celsius, and we're asked what the activation energy is. Well, we've been given two Ks and two temperatures. The temperatures have to be in what units?
Well, the R was in Kelvin, it had Kelvin, so it has to be in Kelvin.
That's right. So I need to take 25, add 273, take 50, add 273. Make sure that for this one, if this is going to be my 323, that's the 50 there. Make sure that this is the second K then, or 4.64 times 10 to the minus 1. 4.61 times 10 to the minus 1. All right. And then I can solve for the activation energy. Natural log of this value here, divided by the value in these parentheses here, and then multiplied by our gas constant. Should give us, divided by 1, then should give us our activation energy. Okay, so let's talk a little bit about or actually this is a good place to stop. We'll